happy that today Danfei Xu is here with us to talk about robotics and his work into integrating machine learning methods into robotics. Danfei Xu is an assistant professor in the School of Interactive Computing at Georgia Institute of Technology, and he received his PhD in computer science from Stanford University in 2021. His research, as said, tried to integrate machine learning into robotics and focus specifically on manipulation planning and imitation learning. He tries to enable physical autonomy in everyday human environments with minimum expert intervention. So I'm very happy to welcome Danfei, and I will give him the floor. Thanks a lot, everyone, for being here.
Awesome. Thanks for the kind introduction. Let me share my screen first. Use my screen. Okay, awesome. Thanks for the introduction and the invite from Ethan, Kush, and Sylvia. Yeah, it's my pleasure to talk about my research primarily, but if you have anything you want to discuss with me or talk about after the talk or during the talk, feel free to do that. So this is going to be more or less a kind of like an overview of one direction of my lab's research. And the talk was designed to be 45 minutes, but I'll try to skip some things in the middle to reduce it to 30 minutes. We'll see how it goes. Yeah, so the title of my talk today is Bridging Reasoning and Acting for Everyday Autonomy. And what I'm going to explain to you why everyday tasks are important, and why bridging reasoning acting is a promising path to achieve everyday autonomy. So my research goal is to build robots that can do things in human environments, right? Like your home, like doing laundry, load dishwashers, put away groceries, and so on and so forth. And they have to deal with also a variety of environments that are different from home to home. So why is this capability important? Well, autonomy in homes are important on its own, but I believe that if we can have robots to do all of these things in all the homes, they are ready to be deployed in scenarios where autonomy is even more critical, like hospital, auto care facility, or like rescue mission, right? So in disaster response scenarios. So the goal is to be able to robot to do these things in a reasonable competence. So how do we go about teaching robot to solve and potentially generalize to new tasks in an everyday home environment? Well, an inspiration we can take from human is what allows us to function basically in our daily lives are not just these individual skills like dicing tomatoes or breaking eggs or this kind of knowledge, pieces of knowledge, right? But also the ability to break down a hard problem into solvable pieces and use what we already know, like kind of connect them together to solve new problems. And because we're in robotics, this kind of sort of ability is particularly interesting to me in the scenario where we want to connect the knowledge to motor actions to actually physically change the environment. And in cognitive science, such ability is broadly referred to as cognitive control, because you use your knowledge or what you know about the world and bridge that to your motor actions. The seminal work from about prefrontal cortex theory or PCT from Miller Cohen defines cognitive control as the ability to orchestrate simple low-level sensory motor skills to generate complex goal-driven behaviors like cooking. Right? As a concrete example, we can contrast tossing food in pan with cooking by following a recipe. So the former can be thought of hardwired reflexes that can be acquired through practices or simply evolution, right? For example, another reflex or pre-programmed to develop is to reorient to the source of sound. And the latter is about the ability to understand like rule of games, right? They're intentional, flexible, and allows us to do things like play a new card game, like navigate a new city, etc. So together, reason and acting allow us to go about in our daily lives and solve old or new problems in the everyday scenarios. And the gist of this has been in robotics for a very, very long time. And one particular framework that I really liked is task motion planning. Basically, the idea is to solve a complex problem by searching for high-level actions like symbolic task plans or reasoning, if you prefer that term, and synthesize low-level control accordingly or acting, right? I've kind of long admired this line of work from Kalen, Garrett, for example, and Mark Jasson. I don't think this video is gonna, oh, it actually plays. Okay, sorry. I think my PowerPoint just crashed for some reason by playing this video. Let me try again. That's odd. Huh. Let me try play video without sharing. See if that works. Okay, it works. Okay. All right, let's back off. Share screen. You see my screen okay? Don't see people's faces. Yes.
Yeah.
Awesome. Yeah, so for example, work from Kalen Garrett on task motion planning on kind of manipulating object kinematically, and also be able to plan dynamic motion. This is work by Mark Chasson, who is thinking about how do we actually plan out acceleration, force, and speed in order to do things like, for example, here, hitting a ball with a bat to our target, right? So this is kind of an amazing complex of behaviors. Although it's only a simulation, it makes literal, it actually solves the problem in a principled manner. But it turns out that TEM assumes a fairly idealized model of reasoning and acting. And so the high-level reasoning often involves some type of logic or search or come with a high-level skeleton, which each step specify some preconditions or goals. And the low level is to control the robot to satisfy this plan, and in turn tell the high-level plan the cost or whether it's feasible to at all. And now to use such a framework to break down a hard problem into solid pieces, we need to manually write down these like precise pre and post conditions and basically write down physics of the world in order to solve these problems, right? So you kind of have to build these complex kinematic trees if you only are solving kinematic problems. And if you want to do like highly dynamic problems, then you will have to write down like complex kind of optimization problem like logic geometric programs and define all the sort of physical conditions like breaking contact, being contact, so on and so forth. So, but although this is highly limiting in the real world, I still believe so that the problem of needing joining reasoning acting by hand is a powerful recipe for solving and generalizing across complex tasks. So what I'm proposing here really is that joint reasoning acting allows for breaking down unsolvable problem into solvable pieces and compose known building blocks to solve new tasks. And we should replicate this kind of general recipe, but develop less restrictive algorithms that has less assumptions. For example, this talk, we're going to kind of go over like the high-level ideas of how do we bridge reasoning acting through learning, and how can we develop algorithms with fewer assumptions, with a few concrete examples. So I'm going to talk about two directions. So assume we have the reasoning symbolic abstractions. Can we do better in terms of acting, right? Can we actually connect one sequence of skills with our symbolic interface in order to solve tasks and generalize across tasks? This is a work we just submitted to ICRA last year. And from acting reasoning, so if we can have skills to begin with, like we know we have these motor capabilities, can we chain them up to solve new problems? And then at the end, for time, I'm going to talk about how do we scale up, like how do we use learning? If we collect more data, can we actually solve more problems, right? And where does the data come from? So And again, this is going to be a high-level overview of these work. I'm going to skip some of the intro kind of details in the middle. If you're interested, you can ask me after the talk or read the paper. Right? So there's a work called LEAP, Guided Skill Learning and Abstraction for Long Horizon Manipulations by my first PhD student, Shuo Cheng, who just joined last year and kind of is already doing amazing work. So let's review the definition for task motion planning in the most kind of generic sense, where this is basically we're trying to solve a dynamic motion planning problem where you have some cost function you want to minimize, and you have some constraints, right? These are basic physics. And if you kind of break this down a little bit further to have individual skills and how their physical properties like pre and post condition connect to each other, you have a sort of a combinatorial discrete optimization and also continuous optimization problem. So it's sometimes known as logical geometric programming problem. So to do this, you have to write down high fidelity differentiable dynamic models. So these models need to be in their analytical forms, and you need to be able to differentiate them through so that you can solve the optimization problem. In other words, if we assume we're given nice reasoning abstraction to break the problem into tractable pieces, we still need to write down these analytical models of the environment. And you can imagine that they're really, really hard to write down for the real world, where we don't really know the underlying dynamics parameters like friction and masses and acceleration and all these things. And it's going to be especially hard to write down for contact-rich manipulation tasks, like inserting something with tight tolerance, operating constraint mechanism like pulling a drawer, and tasks that combine these, right? Like using a Keurig machine, for example. So can learning help? This is the question we ask in this work. Well, we could learn these models of these individual pieces. There's a whole line of work from folks like Mark Desson on how to learn these models in simulators and how to deal with imprecise models. But we are not going to do that here. We're going to resort to a model-free approach for these individual skills. So, and try to directly learn motor skills. And so the first part of the work is about to learn motor skills for TEMP system so that we can extend the set of tasks that TEMP can do. So how do we learn these policies? Well, recall the goal is to solve a complex long horizon task, and we don't want to assume any skills to begin with, right? We don't know any of these skills. So, and it's still very expensive for us to set up the right initial state for each skill at the correct stages of long horizon task and repeat again, like do some RL-based learning, right? And the second question is, we need to answer is that how do we make these learned skills more generalizable? And because it seems like it's wasteful just to learn skills for a single long horizon task, and can we make them as generalizable as the sort of the physical model of the things we had to write down for task motion planning problems, right? So, so how do we actually learn them, and how do we make them generalizable? This is where the learning by TEMP system. So to answer the first question, we'll basically use TEMP as the automated skill curriculum. So as you know, for curriculum like ML research, we progressively introduce harder and harder problems so the system can learn the whole thing. And here in long horizon tasks, we're basically going to use progressive growth skill set guided by task plan and use proficient skills, the skills we already learned, to reach the preconditions or the states that the next skill can be executed of less familiar tasks. And then we schedule the less proficient skill for learning in the next iteration, and it repeat until all the necessary skills are mastered and task is solved. So I'm going to show you kind of a flow chart of how this is done, but we're going to actually go on to answer the second question, which can we make the learned skills more generalizable, right? If you treat this as an RL problem, you can learn individual skills, but there's no way that we can say that this is going to have to achieve strong generalization in a new situation and with a new object, for example. Right. So what's the idea? So here we can take a look at how task motion planning defines skills, right? Skills are basically these kind of symbolic operators that has their, like, imagine a function, right? You have signatures of pre and post condition, where what does the condition needs to satisfy in order to reach this symbolic goals. This is very useful actually for RL because in a temp system, we assume that actions are lifted, meaning that they can be just plugged in to a new problem, right? If you have this O, which is an object you want to pick, and a robot R, and you can just plug it in like calling a function, if you satisfy these assumptions, you can actually execute them. But the underlying model is incredibly complicated, and you have to write them down. So the idea really is that can we actually use these symbolic definition to constrain the space where the RL can happen, right? So if we can actually introduce a abstract state space for the RL problem, we can actually make them kind of at some level be able to generalize across object, tasks, and domains. So in other words, can we enable learner skills to have a similar level of generalizability than these symbolic defined skills where we have an analytical solution under the hood? So this part of our method will be using temp as a guidance for state and action abstractions. So the first idea is to use a skill symbolic operator to determine task relevant state space for skill learning or RL in general. For example, if you want to insert a pack into a hole, the only thing that's relevant here is not the color of the table or the color of the wall or how the robot looks like, but rather where the pack is and where the hole is, right? Their poses and maybe their shapes. So we can introduce a reduced state space just by looking at a symbolic definition of a skill provided by a task planning system. And we can use we use these precondition effect to determine when a skill is executable or should stop. So we can delineate the range of states that they should be applied to. And finally, we can use pre-post conditions actually as a skill reward function to train these RL files. This is a desired state we want to reach. So we're actually going to use these definition to generate reward function for RL to happen. So in other words, the final P, after the planning domain provides a state and action abstraction for learner skills. And the last piece is that one observation we can make is given some kinematic model of the world, the free space motion is easier to deal with than contact-rich motion, right? So we can actually have a motion planner in a loop to facilitate the RL pulse to get to the right initial state to start the contact-rich kind of skill learning through reinforcement learning. And so the skill can focus on the contact-rich part of the task instead of everything, right? Free space motion, learning free space motion through RL is wasteful. So combined together, we have the for and by, so learning motor skills for and by temp systems. So the summarized key idea is to learn contact-rich manipulation skills to expand the capacity of temp system and use temp as an automated curriculum for progressive skill learning and use temp symbolic skill operator as guidance for state and action abstraction. And last piece. So I'm going to quickly show you a flow chart of this. So given the symbolic skill operators and task planners, we're going to give a goal to the task planner. Task planner is going to generate some plan. And given a symbolic skeleton, we're going to initiate some, and given the proficiency that we'll observe by actually running these skills through RL, we'll get some, for example, average reward. And then given the reward, for example, this really low reward, we'll get actually schedule it to do reinforcement learning and until it can actually go reach this precondition of the next skill and then use that to learn the next skill and so on and so forth until the whole system model, the task is mastered. And then all of these skills are now, because this is how we define it, they're actually reusable for other tasks. Okay. Let's look at some results, right? So let's look at how a system evolves, like how the system actually learns these skills throughout, like the simple task, which is to pick one hammer and place into one drawer. So has to open the drawer and place the hammer into them. So this is a progress where the x-axis is environment steps and y-axis is the skill proficiency of that particular skills, and we'll color code the skills. So in the beginning, the model will actually the system will try to learn these learn the open skill, right? Learn to open the drawer, and they will not be able to reach the initial condition of the picking, which is well, this drawer should be open, and then once they start to be proficient of first skill, it should start to learn to pick the hammer, and then place, and then finally close the drawer to complete the task. So that's one piece of a longer horizon task that it gets to learn. And then you can see the sort of learning curve compared to other hierarchical method and so on and so forth. That, for example, we can learn to insert pegs, 2 pegs into 2 holes, and insert and do the 2 hammers. So basically, there are 2 hammers, 2 drawers, and we can kind of place them into these drawers. I'm gonna skip these part as a little more subtle and look at some generalization. So we can actually generalize these skills to achieve new symbolic goals. So given a new symbolic task goal, it can actually generate a new plan. And because the plan, that each individual skills are like functions, right? They have signatures, and if you just plug in the right argument, they can, in some sense, generalize to some extent generalize to new situation that you ask it to do. So, and we can do the same thing for hammer place, like place a hammer into a different drawer that it started with, that is trained with. And also can also deploy this onto real robot. There's crazy amount of engineering in this. This is not really straightforward symptom transfer. There's a lot of underlying things. It's just to show that policy works on the real robot. Yeah. So one last piece I want to mention is this cross-domain skill transfer, because eventually we want a robot to be able to learn the skill in some environment and transfer that to a new environment, right? So we show that this actually we can show some initial results for that. So if we can learn the pick and push and pull skill from other domains, like for example in hammer place, we can actually generalize this to a new domain, which is this task of using a Keurig machine, right? So open a drawer, can play this again. Yeah, open a drawer and pick up the coffee pod, insert the coffee pod into the Keurig machine, and basically close the lid. Yeah, then you can see that the free space motion is straight line because it's motion plan. Other cases are more kind of jagged motion is RL. You can see the training curve and all. So there's a large gap. So in summary, if we we can relax TEMP's model-based assumption and solve contact enrichment inclusion problems with having a dynamic model. And on the other hand, TEMP gives us abstraction. We can abstract away unnecessary details and also provide a pre and post condition signature for each RL policy so that it can be composed together by a symbolic task planner to solve a long horizon task, compared to if you just do monotonous just RL policy. Yeah. I can take any questions here, if there's any. And most likely skip the next part because we're at.
Is there any question? There is no for the moment. Okay. Like you can continue, and then we can ask in a few minutes when you are done with this second part.
Sounds good. Yeah. So the second part of the talk is about where does planning abstraction from it. So where does the reasoning abstraction? How do we actually plan with skills, right? In this section, we assume that we know the skill abstraction, like the symbolic definition of a skill of a task planner, but where do these come from? So the next part is really about, given some motor skill, like motor primitives, like picking, placing, can we learn suitable abstractions that we can use to plan towards a goal? So I'm gonna go really, really quickly through this part because I mean, we're at time. But the key idea here is that predefined. We start with some predefined manipulative skills, and we want to plan towards goal. We want to reach towards goal by picking the right skill and their parameters, the continuous parameters, like where to pick and how to pour and how do I open the drawer. Why did I? Oh, sorry. I think I clicked it up. So yeah, and then traditionally, I mean, task motion planning, again, we need to define all of these properties like shape, like these predicates and effects and all these transitions, right? Like what is the preconditions that allows these skills to satisfy some effects? So we're effectively learning a transition model of the world by assuming we know the underlying state of the world. So the question here is that can we learn a planning reputation or transition model on the skill level? So so this is what the skill looks like. So we're going to choose skills, individual skills, and the parameters, like how far to pull the drawer and where to grasp the handle and how to grasp a mug, right? And then the goal is to be able to chain them up in order to achieve some goal. And it's a really hard problem because if you choose the right, like slightly wrong parameters, you'll miss some, for example, miss the opening drawer skill and fail to achieve the entire task because the first step it failed. So the problem is that we want to learn a transition model. So I'm going to explain, kind of skip the motivation here. So the key idea here is that we want to learn future skill affordances, basically feasibilities through trial and error. We're going to try different sequences of skills and learn about their outcomes. So like, what does doing the first skill enable us to do next? And then use that experience for planning. So in planning, we need a predictive model before we actually do something. And here, by collecting a large amount of experience of what first skill or the second skill allows us to do the third or fourth skill, allows us to build a minimal representation of the transition model. Here's a sort of an explanation of this. So if we choose one set of parameters going to allow us to do something, and other parameters will fail to allow us to do the next thing, which is to place a mug into the drawer. Right. So if we don't open the drawer for enough opening, we'll not be able to place it. And by kind of trial and error, and we can actually learn a sort of level set or like a predictive model of the feasibility or affordance of skills in the future. And this transition model is minimal, it's latent. So we basically have a latency model that gives us this kind of transition probabilities in this latent space and can be decoded into actual feasibility of certain skill. So you can query arbitrary skills. Can I run this skill in the future, given that I have run that my plan is this sequence of skills so far? And we can show that the plan is feasible, the whole plan is feasible, is roughly equal to each individual skill is feasible. And then to plan towards goal, we'll basically query the model again and again until we find a high enough success rate for last skill to achieve the goal. And then we'll run this in a trial and error method. We'll try things out, get some feedback, and do this again. And because we're using deep model to predict future affordances, we name our model Deep Affordance Foresight, or DAF. So here's a very simple example where it actually learns to use tools to stack two blocks. So the red block is behind some kind of invisible curtain that can actually reach directly. So use tool, and then the other cube is inside a pipe. So actually use the tool differently in order to achieve that goal. And here, because the next skill it needs to do is different, it actually the robot actually learns to grasp, basically choose a different theta for that grasping skill in order to run the future skills. And if you look at how the learning evolves, at a 1,000 episode, it actually learns the precise grasp that it needs to use in order to use the tool for two different situations. And finally, we can test on this kind of get coffee task. Is an integral part of my thesis research. making coffee. And you can see that at episode 100, or just try random things, is not really kind of doing anything meaningful. And the 500 episode, and can actually already start to kind of do this, but violently kind of throw the coffee beans into the coffee machine. And 1,000 episodes, it will actually learn to do a reasonable job by not spilling too much coffee beans into outside and make coffee. And we can also show that it can fast adapt each of these skills to a new environment. For example, we can learn a simple task, which is get tea, and transfer some of the skills to get coffee. I'm not gonna explain this in details, but yeah. So the takeaway for this very short section is that we can actually learn a compact word model of how we use skills and use these models, use models for plan for long horizon tasks. And the word model is modular because the affordance is really defined independent of what you want to do eventually, but rather how likely can you chain this with the next skill. So these pairwise chaining is modular and can be transferred to learn new tasks. And finally, very, very quickly, how do we scale up? How do we scale up? So all of these are nice formulations that you can run on small problems, but how do we actually achieve library autonomy by acquiring a lot of data and a lot of skills? Like what the rest of raw learning community is saying, is a data problem. So we actually need a lot of data in order to do this. Just more data. But under the lens of acting reasoning, there are actually some interesting observations to make, which is that acting and reasoning require different type of data and may be collected from different sources. For example, acting is how do we collect embodied, diverse, and high quality experience data, and how do we make best use of the data for generalization. And for reasoning, we may not need embodied data, right? Just thinking about where like coming with a solution for a task doesn't require you to actually try something and to handle physics, right? To try to understand the physical phenomena of the environment. So we may be able to learn from unembodied data sources. And can we make use of general reasoning engines that I'm going to show later. So we have a bunch of work on imitation learning on how to collect more data better, and how to study the right architecture to learn from human data. And one particular thing that I want to highlight is this framework called Robot Mimic that we published in 2022, Coral. So we did a large-scale benchmark of basically BC, behavior cloning, versus offline RL, and basically all aspect that matters, like what is the architecture that matters, demonstration size, the quality of demonstrations, what is observation space. So we did a whole bunch of study and released everything out there. So it's an easy to use modular framework that has all the data sets and everything out there. So if you're interested, or if you're working in imitation learning or offline learning for manipulation problem, check it out. It's been there for a while. So we kept maintaining it and making better. And the second piece is reasoning. So how can we learn reasoning from a variety of data sets, for example, from video data or from like general, like for example, we did a work on how to formulate task planning as a neural programming induction problem, right? So one thing I want to highlight is our recent work on use large language models, general robot control programs called prompt. So the idea is to kind of write Pythonic and syntax to control robot by using large language models without actually any training. It's just prompting. I think this is a fascinating topic, not just because we can generate Python programs, because it encompasses the two sides of reasoning. One is before we have these type of models, we need to separate reasoning mechanism, like first order logic, from knowledge, right? We define the abstract operators and how the world will evolve given some symbolic operations. But now LM has a lot of common sense knowledge and also appears to be able to do some sort of reasoning to come up with a plan. So can we actually make a better connection among them, and how do we bridge them to the continuous control side? I think is a hugely exciting topic. Okay, so I want to conclude talk by kind of summarizing. Actually, yeah, so the last piece is scaling up may require diverse data source and knowledge sources. And here are the two works I presented. And if you're interested in the first work, email my student Shuocheng at gatech.edu. If you're interested in the second work, just email me. And yeah, that's it. Thank you.
Thanks a lot, Danfei, for the talk. Do you have any question? Is there any question from the audience?
Ask a question.
Yes, sure. Go ahead, please.
I wonder, because affordances are symbolic, while skills are more like motion planning. How out of learning skills, which are learning motions, suddenly the affordances appear?
So,
Do you...
go ahead, sorry.
Yes, go on.
Yeah, so that's an excellent question. So I think the traditional affordance sense, like you can use this cup, you can use a handle to lift up a mug, is semantic, right? We would kind of consider that as a semantic knowledge of all the world. But at the end, if you want to acquire a large amount of these knowledge, you actually have to try it, right? This affordance is all about be able to do something physically, and it's constrained by real world physical phenomena. And we can collect a large amount of these data by asking people what they can do to a certain object, but eventually this is not an exhaustive list. And for in a specific situation, you might need to actually try it out, to try things out with some skills, right? Can I pick this up? This picking skill has some physical properties, some motion plans, some trajectories, and does this particular trajectory allow me to do this particular thing, which is we call affordance.
Do I understand correctly that those affordances do not somehow emerge from those motions? You have a set of affordances and you simply connect them to the motions, yes? Is that correct?
So it's connected in a sense that motion, we define affordance based on the specific motion we're gonna do. So does this object afford this particular motion, if you call skill as motion?
Okay, so maybe I will reword what I have said. Let's say I have a drawer with a handle. And having this handle, I have an affordance. It affords me to open the drawer. So this affordance is somehow known to me, but how to pull this handle is unknown, and that I learned. Is that correct?
So I think this is from the human sense, I think this is correct, but from robot senses, this is maybe not, because robot may not actually have the right morphology to open that drawer. So it may not be known to the robot that it can actually open the drawer until it tries it, right? Maybe it has a weirdly shaped gripper that prevents it from manipulating the drawer. So we're really talking about like not really a semantic concept known to human, but rather what robot can do already. Like it's limited by the capability of a certain robot.
Well, that I understand. I understand that the kinematic constraints of the robot might be such that it won't be able to pull the drawer. Yes, yeah. It might lack the necessary number of degrees of freedom, for instance. But what I want to establish is whether those affordances, in other words, the idea that the drawer can be opened, pre-exist. And then once you know that such a thing is associated with the handle, you need to try to learn the skills that will execute this affordance. Am I correct?
Yeah, that's an excellent point. Yes, I think the prior about what a skill is promising in what region, in what state is a known. We can't try a certain skill on anything, right?
Okay,
So,
then what is the mechanism that finally associates this particular affordances with this particular learned motions? Do you do it by hand, or is there an automaton that does that?
So if you're talking about how this particular knowledge about this is promising, like opening is promising to the actual trial and error, like initiation of trial and error, that is hand defined. But if you're talking about the specifics of how do we, once we learn these, like what is the form of the model we learn, and how do we connect these individual affordances together to achieve a long horizon task, that is learned. That is came up by the machine learning model. Yeah.
Okay, thank you very much. I get your answer.
Okay, thanks a lot. Do we have any other question? You can also write in chat and we can read it for you if you cannot talk, if you prefer that. Okay, then I'm gonna ask a question. So I was wondering, what is the relationship with the work that you have done in both the work you presented and imitation learning? Because you talk about reinforcement learning, and I wonder if there is, like, maybe I missed the part, or I didn't understand well, where is the part of, if there is a part of imitation there, or if just there is a different way of finding different way of representing the task and reasoning and acting according to that. So are you, if there is an imitation, like if the imitation learning part is integrated somehow, or if you have worked on, because in previous work you have done that, but I think in this last work you haven't, right? And I was wondering why you moved it out from imitation learning, especially considering that you're working on complex tasks and getting to learn them from scratch. It's quite hard, and as you said, one of the main problems is that we need many examples. So I was wondering, why did you move out from imitation learning and from other ways of learning that might help also find a way to encode the task?
Yeah, good question. So I think the reason is that, I mean, the problem with it is because of specific problem definition or problem statement we have. Planning is to be able to anticipate what's going to happen in the environment given some action, right? And this anticipation requires counterfactual reasoning. Like, we need to understand what's the alternative, what is bad for this sequence of action. Imitation learning doesn't give you that, or most likely doesn't give you that.
But you could build a counterfactual representation from the demonstration of another agent, right? Because you could say, like, and this is also connected to my next question. You actually touched this part of the counterfactuals, because you said, like, one of the challenges also being able to generalize what we have learned, right? And to have a more abstract representation, and also to know what is the hierarchy between the things that we need to learn, right? So there are certain skills that are needed, and some others that are needed first, and some others that are needed but after having developed the first ones, right? So can we have these counterfactuals from the demonstration of another agent, and can we build those counterfactuals from another agent, and then based on that better generalize?
Yeah, that's a good question. I think this recent kind of like learning from code, I'm not sure if you got it, I think it's going towards that direction. So instead of saying that we are collecting data for a specific task, we're just going to say, okay, demonstrate in an environment. It will not necessarily give you like all possible things you can do, it already gives you a good coverage of like what you can do and what are the meaningful things, and you can think about them as counterfactuals, like on the sort of a meaningful action manifold. But if you're talking about like say, oops, I dropped this block, the human may never have demonstrated this and consider that as meaningful. So you may not be able to encounter that. So I think this question of like, what does the specific robot can do and will fail, it will highly influence what data is going to be helpful for this robot, right? So I think there's I would say, still a gap between what humans data can provide, what other technology data can provide, versus like what's actually useful for the specific agents. Just because we're dealing with sort of precision problem, right? If you fail at a certain step, it's catastrophic, and you will probably not be able to advance. So like 90% success rate is not good enough. So that's my perspective. Like there's still a gap between active exploration of both what it's able to do and what it will react to you, and the static data set.
I see. I think I would continue asking, but we have another question in the chat. So let John, do you want me to ask, or do you want to ask yourself? Okay, so
I can read that. I see it. So I'm curious, what do you see the role of languages for robotic manipulation, or more general? That's an excellent question, because I mean, in theory, language does not connect with motor. There's no direct connection. Like pick up something provides so little information about actual motion of picking that. Probably I think I don't have a good answer for that right now, but intuition can help mostly with task planning right now at the state of research. Maybe once we have dense enough data set that has level of coverage of language, we can actually kind of learn a growing space of language action that, first of all, for a task planning system to better communicate with a motor system, because language is a lot more powerful. Natural language is a lot more powerful than structured symbolic planning definition. You can describe more things like move a little bit to the right. Right? And the second part is the compositionality. Like maybe you can carry some sort of structure, but I have no intuition of that. Like how does that might work? Is that hope that's going to happen?
Okay. Are there any other questions? Yes, we have a question from our son. Can you read it, Danfei?
I wonder if we have a look at Google papers. I mean, it's very similar. So what we did here is pretty much like a kind of a variation of that. So this is that we constrain the amount of action that auto generate, right? Without syntax. There's free text plan generation that give you random things that you are not. It doesn't map to your action. So I think kind of. And another piece is the motion part, like the actual motor primitive. So I think the latest system they use basic behavioral cloning to learn individual skills, and here is more hard coded. But kind of looking to the future, I think that's partially how that in my last answer, which is we're still not clear how StateCan-like system is able to, on one hand, help robots solve harder tasks. Because if you think about it, generating a task plan is not terribly hard if you can actually sit down and write a plan for it, right? It's not that hard to solve a single task. Maybe the appeal is that you can solve more tasks automatically by just providing a goal, but it's not the biggest gap. So I think the question really is like, where does this value of having a kind of reactive reasoning engine buy you, basically? And that this reasoning engine has the internet knowledge about the world.
Okay, great. So if you have any other question, we have a Slack channel, and you can join the Slack channel. Let me share with you the link tree. Talking Robotics. Yes. So here you can find all our links, and there should be no. Can you please share the Slack channel? Yeah. Okay. Well, I'm gonna thank once again Danfei for his talk. It was really good and super interesting. I invite all of you to read his papers and to keep chatting about this on the Slack channel. I'm gonna now share my screen again to present the next speaker. So let me share it from here. Yes. Can you all see my screen? I hope yes.
Yes.
Okay, so our next session, which will be the 51st session, we will have Taylor Cassell Falkenkerner. I hope I didn't mispronounce it. And she is from University of Washington, and she will be talking about enabling robots to adapt to and learn from real people. So hope to see you all there. It's on the 25th of January, so see you soon.